All right. Welcome everybody to week 4 of the competitive programming club. So a couple things. No animations this week, sorry. I just keep getting busier and busier. Actually, I an REU that I did over the summer, the paper that I did for it got accepted at a conference, so I've been um, just been mainly focusing on that. And it also, the conference is 4 days after ICPZ, so it's just gonna be like back to back chaos. But I'm really excited for that. But yeah, I haven't been able to fully complete. Um, I wasn't able to do the animations, and I also don't have any code to show for you guys. But I think that that's okay because the problem that we're gonna go over is mostly just concept, and I guess I can start by showing what we're going to be going over. Oh, I didn't set that up either. Here we go. Okay, so even substrings. There's a lot of really good concepts in here. So, and this was a pretty formidable ICPC problem. So I thought I would just try to break it down and go over the main concepts. So you're given a string, one index, 1 through n, consisting of the first 6 lowercase English letters between A and F. So A through F, lowercase letters. A substring is called even if every distinct letter in it appears an even number of times. So like A, B, B, A, right? That's going to be an even substring because all of the characters in it show up an even amount of times. And then, for example, in A, B, B, I, C, A, for even substrings. If a same substring appears at different locations, they should be counted multiple times. For example, AAA has 2 even substrings inside of it. You are to process Q queries of the following 2 types. Given a range specified by 2 integers L and R, count the number of even substrings between S, L, and R, inclusive. Both ends are inclusive. The substring starting at SL and ending at SR. And given an index I and a letter X between A and F, change S of I to X. So this is quite a monster. It's got a lot of things, and if you look at the input size, we're working with n of the string length of about 200,000 and about 200,000 queries. So if you guys remember from the time complexity checklist or like lookup table, anything that is above 10 to the 5 is going to be n log n or O of n. It's going to have to be. So what we're really looking for is some kind of n log n pass over the string, and then n log n for all of the over all the queries. So each query will have to be log n, right? Oh, well, I mean, you could do n, but I don't even know if that's possible. So we want 2 n log n passes. So if you guys remember from last semester, those of us who are here, this specific format, the way that this question is structured, which is a little weird, right? You're doing multiple queries per test case. This implies the use of something called a segment tree. And actually, I'm not just gonna go right into the segment tree. I'm gonna build up to it. So let me switch to camera. Okay, so I'm sure you guys remember when we did prefix sum. It's a pretty simple idea, but I'll go over it again. So for example, if we had 5.
You're too high on the board. You
Okay.
can't go like your height.
You're right. And there's a erase over here. Got some work done. So let's start with a prefix. I'm gonna try to keep everything on the board too. So call this prefix So we start with some array of numbers, say 5. Yep. Let's make it bigger. 5, 1, 3, I don't know, 7, 9. I want to make it a power of 2, 6, 7, 8. Okay, so if you're asked to, for example, um, find the sum between an arbitrary subarray, an arbitrary range inside of our main array, right? We know the trick is to, let's say we have q queries, range queries over this array. The naive solution would be to just sum them up, right, for each query. But if we do a prefix table, which is going to pre-compute the sum from 0 to I for every I, including, we're always going to include a 0 for the empty subarray. And let me just do that. So it's going to be 5, 6, 9, 16, 25, 25, 27, 28. Looks right. Okay, so now the trick is, right, if we want to find, like, if this particular index, for example, now gives me the information of the sum over this entire range, right? But if I want to get it for an arbitrary range, not necessarily starting at 0, the trick is that I just find the window. Let's say I want to start from here to here. Well, I can take this range, right, which is signified by this guy, and I can subtract from it this range, right? Because that will leave me with the desired range, right? So if we try that now, if this is L and this is R, then this range is given by prefix of L minus 1, right? L minus 1 inclusive. And this range is given by prefix R. So when we subtract them, call it P of R minus P of L minus 1, we're going to get the desired range, which is going to be our sum over L to R. And we can do a quick example, right? Obviously, 7 plus 9 is 16. So, so when I grab this range 25 and then subtract from it 9, we should also get 16. Okay? So that's like an example, but by construction, we're subtracting these overlapping prefixes to get an arbitrary subarray. And this is O of 1, right? Because we're just grabbing an index here and grabbing an index here. For each query, that's just 2 operations. Two memory lookups and a subtraction. So it's going to be constant. So now the next question is, what happens? Oh, sorry. I should mention that there are some requirements for the operations that you can perform on the prefix table, right? It doesn't necessarily need to be addition, although it is commonly addition. What you need is 3 things. So let's call this our operation. Okay. It needs to be associated. Why? Because if we do, for example, the operation like if we want to do this prefix idea in general, right? Then what we're really saying is that the sum at I is equal to the, let's call this A, is equal to A of I plus A of, A of 0 plus A of 1 parentheses plus parentheses dot 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 plus. So you see, when we do our when we do our rolling, this is called a fold. When we do a fold over this array to get a rolling sum here, we need to make sure that the order of the parentheses would be the same as if we just did it all straight down like this. And in fact, addition is an obvious example of associativity. So that's why we need associativity. The next thing that we need is an additive identity, because additive, not referring to addition, but in algebra we call it addition, but we're really just talking about whatever binary operation, right? But we call it the additive identity, which, what's the additive identity over addition? It's just 0, right? Because anything plus 0 is itself. But like I said, this doesn't have to be 0 per se. It just needs to be that whenever you do this operation with it and another number, it's going to equal itself. Then this is really just an intermediate step, because what we really want are additive inverses. Think about it. If I'm going to subtract this value from this range, there needs to be the concept of a negative value, right? So in this case, we're subtracting by, we're taking this value, 9, and we are multiplying it by -1 to get the inverse. And so those obviously need to exist. And an additive inverse, we call it x to the -1, or sorry, for additive inverse is just, shorthand is just negative a, right? And those are the 3 conditions for this kind of prefix table idea. Now, the next idea I wanted to get into is, okay, this is great for, we did O of n to create the table, then it's O of 1 for all the subsequent lookups, right? That's great. But what happens if we want to update a value? Okay, so now we have this original data, and we have our prefix table. But let's say I want to change this guy to 0. Okay, what I've done now is I've destroyed everything from here onwards, right? It's now, all of this data needs to be updated accordingly, right? Because they all contained that value in their range. So you can imagine, in the worst case, if I'm updating this guy consistently, it's going to have to do a linear scan, an O of n scan, to update all of those guys, right? So for this simple prefix sum table, O of 1 lookup and O of n update. Now, what happens if we cut this table in half? What I mean by that is, I'm going to get rid of this. Sorry. Instead of having one prefix table, we're going to split it up right down the middle. So we're going to have O, 5, 6. Let's use 0 now. So 6, 13, and then down the middle, we're going to start over. So we're going to do another 0, and then this is going to be 9, 9, 11, 12. So this is weird, right? We have to deal with 2 tables now. But the benefit is, let's try querying a range over this new table idea. if I wanted to do, first of all, if I want to just query something in this range, right? It's the same as the before, right? Because we're not divvied up um, across two tables, right? It's just going to be the same as the original prefix table. But the real sauce comes into play when you have to query across the tables, right? So in this case, what are we going to do? We want to find the range from here to here. Well, we're going to have to do a little bit more work, right? So if we're going to subtract this range from this range, we don't know what this range is yet, but what we can do is we can create two more pointers. So we're going to split down the middle here and here, and we're going to grab this range, which corresponds to this value, and we are going to, so that's fine for this value, right? 6. And then, but for the rest of the range, we want to add this guy plus this guy, right? Does that make sense? So we're going to have our total of 25. But we had to split it across by putting two pointers along down the middle on the two edges of our two tables. And then, so I put 25 here, but really what we're doing is we're doing 13 plus 12, right? And so in total, the operation is 25 minus 6. Minus 6 is 19. Okay, and then let's check, make sure I didn't make any mistakes. 3, 12, 19. Okay, so why did we do this? It took longer to query, right? Than it would have normally. However, the benefit is that we've gained time savings in the update, right? Because now, let's say I want to update 5 to 2. I don't have to propagate any information into this table, right? The propagation ends halfway because we're starting over here. This table only considers these ranges. So what we gained in query time, we saved in update time. Okay, so that is the basic idea behind these kinds of trees, like Fenwick trees and segment trees. Is they bring this splitting idea to its logical conclusion of recursively um, splitting these ranges um, into halves, so that we can um, balance. We want to find a balance between updating and querying. So what does that look like? Well, we're not going to go over the Fenwick tree, which requires those associativity, additive identity, and additive inverse that I mentioned before. But we are going to go over the segment tree, which is looks a little bit different. So what we're going to do is, I should have just kept that on that table there. Actually, let's call this segment tree. And how am I doing on visibility? Is it like, okay? Let me draw even bigger. Let me not be afraid to take up the whole space. So I'm gonna write the array down here this time. And I'm not gonna make it a power of 2. Let's like length power of 2. So let's just go what did I have? 5, 1, 7, 2, 3, 5. All right, so that's 7. So here's the pattern, okay? With a segment tree, we're going to make a we're going to make a perfect binary tree. What is a perfect binary tree? Every, except for the leaf nodes, which have no children, right? Every node is going to have two children. So it's going to look like a nice triangle. So how do we do that? In order to do that, we need to have a power of 2 as the number of leaf nodes, right? Otherwise, we'll be missing some guys. So what we'll do is, so for the segment tree, remember I said the prefix table needs associativity, identity, and inverse. The segment tree, it needs associativity for the same reason as the prefix guy, because we don't know what order of operations we're going to be doing things in, so it shouldn't matter. And we also need that identity, because what we're going to do is we're going to pad out our array to the nearest power of 2. So we have 7 here, so it's just going to be one more. Right, 1, 2, 3, 8. And right, because we're doing plus, so the additive identity is 0. And so the main idea is for every group of 2 and onwards, we're going to apply the operation that we want, and it will basically represent the aggregate operation over that interval. So let me just explain. Let me just demonstrate by doing it like this. So this is our segment tree. Why do we do it like this, right? Remember, it's that idea of querying fast and trading and updating fast, that trade-off between those two. So let's say I want to query some data. Let's say I want to query from here to here. Okay. Well, we don't actually have to do any kind of scan down here, right? Because this interval is completely encapsulated in this node right here. So instead of having to go across the tree, it's just a single lookup on the tree like this. And actually, let me get into the details because it's the time complexity for lookup and update are both log of n, and I'll show you how it works, because things start to get a little tricky if you notice. For example, if I want to query this guy to this guy, this does not fit cleanly under a parent node, right? We've got this guy as part of this whole other subtree than the rest of these guys. So what is the idea here? Well, remember, our binary operation is associative. So we can just start accumulating elements into some kind of like a result buffer or something, whatever you want to call it. So what I'll just do is I'll initialize our result to the identity, and then I'll apply the operation with the identity and this single element. So how the query works is, remember, the query is going to pass in a left and a right pointer, right? So we already get these for free. So here's how the algorithm works. If we're on the left, if we're talking about the left pointer, and we're on an odd number, so if we start 0, 1, 2, 3, that means that we're sitting halfway between a clean interval. So for every odd left pointer, we're sitting on an odd interval, so we're not able to just go up to its parent and grab that information instead. So if the left pointer is ever odd, we need to grab this information. It's not going to be the interval does not include any higher order intervals. And then you want to move, once you've incorporated this value into your result, you want to get it out of your query range, right? Okay, so what I just did was, right, if left is odd, append it, apply it, accumulate it into the result. and move right. Down here, it looks like I just moved one, right? And in the tree, I'll be moving one per layer, right? So in general, it's going to be one across its layer, which corresponds to moving the entire interval out of that range. For example, if the left pointer was right here instead, then we would move to 8, which knocks out both of these guys. So the remaining algorithm goes like, so we said L must be even. If L is odd, apply it, then shift right. If R is, so yeah, we said if L odd, do that. If R is even, then the same symmetric argument applies. So in fact, I'm going to change the query to something like this. So now you can see this guy does not fit cleanly into a higher order interval. So we need to take his value into account. And move left because we want to narrow our query range by the number of elements that we just incorporated into our regime. So now we have this. And now that we've done that, we go up a level. So both children go to their parent. That's how the algorithm works. And now, if L equals R, we know we're at a node. There's no more intervals to worry about. So we just take this value and we add it. So that's 8. And that's going to give us 11. And what was my original query? I changed it from here to here, right? 6, 9, 11. So this checks out. So that's how we query a segment tree. And now let's talk about updating. Now for an update, the way that it works is that when you change a value, so let's change 3 to 1, clearly all the intervals that contain the 1, so that will be this guy, and this guy, all need to be updated accordingly, right? So the rule is that you just apply whatever change it was. So 3 to 1, that's a -2 change. So we'll just apply -2 to these guys. So update's much simpler than the query, but you can see how, at worst, when we do an update, we need to traverse the whole tree, and we will probably, we will need to traverse the whole tree upwards, which is for n nodes, right? That's going to be log of n updates. Okay. So what am I doing? Oh man. Okay, so okay, let me just skip this part because that's not as important. Let's get back to the actual problem. Okay, so the even substrings were asking us. All right, so we have a string. What was it? A, B, B, A, C, A, C. And we want to know, we want to be able to support queries and updates in n log n time, right? So we want to do one n log n pass, and then a bunch of log n queries over the total number of queries. So that should be triggering alarm bells in your head that we're going to need some kind of segment tree. But what kind of segment tree is not immediately obvious? And this stuff is beautiful, I have to tell you. So let's just do this like by hand real quick. So let's say I'm querying from here to here inclusive, right? I want to know the total number of even substrings, right? So what does that mean? So let's just brute force it, right? Scan, 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 found one. A, B, B, A. Okay, continue. A, B, B, A. No, sorry, that's not correct. So that'll be it from starting from A. When we go starting from B, we're going to get BB, and we're also going to get BB AC AC. All right, and then B AC AC. Nope, AC AC. So starting from there, we're going to get that. C no, AC no, C no. So that was an n squared algorithm that we just did to find the total number of substrings. And so we don't want to be doing n squared for all of these queries. We have to bring this down to log of n. So how are we going to do that? So the first thing you should notice is that we don't care about the actual number of letters. We only care about if the number is even or odd. Okay? So in other words, we care about the parity of the frequency of these characters. So I want to. So what does that mean? So we're only working with the integer or the letters A through F, and we only need to store 0 or 1 across a given substring for these 6 values, right? So we can literally store that information into 1 bit per letter. So that's exactly what we're going to do. We're gonna store a 6-bit integer. Well, we're going to store an 8-bit integer. 6 bits will be relevant for our task. So, for example, and then what we'll do is we're going to basically remember the prefix table I was telling you about. We're going to create a prefix table over string parities. So let's do that. So let's create, and this is called a parity mask. So I'm going to call it M. So for an M, just like the prefix table, is going to have the empty string, the empty prefix at the beginning. Okay. So for A, right, that's going to be, and in fact, I have this in, I guess, little endian right now, but it will be big endian the way that I code it. But so look, so let me just switch that. That feels cursed to look at. But so A is 1, because there's 1 of them. We're going to store 1. A to B is going to be 1, 1. What's that in binary? It's 3. So now let's, we have another B here. So that's going to be 1 more. That's going to bring us back to even. So that is a 0 there. So we're going to go back to 1. Okay. Now, what I want you to notice is what I'm doing is addition, right? Pretty much, right? But we're doing addition mod 2, which means that whenever we add, we are going to be either, whenever we add something, we're only going to be essentially flipping the bit, right? We're never going to do any carrying or anything like that. What's a nice operation that flips bits over just a number?
XOR.
XOR, exactly, right? So we will be treating XOR as our binary operation, okay? Over this prefix table. Now, remember, we needed associativity, additive identity, and additive inverse. So let's go over that one, right? What is XOR associative? Well, let's think about it. If I have A, XOR B, XOR C, maybe I'll just do a concrete example. So if we have 1 XOR 1 XOR 1, okay? If I were to do it, just read it down left, right, 1 XOR 1, 0, XOR 1 is 1. Now, if I were to do it like this, we're going to have 0, 1, 1. So this isn't a rigorous proof by any means, but that's an example of XOR's associativity property. So that's a check there on associativity. The next thing that we need is the additive identity, right? Well, that was that you could have noticed that in the previous example. 0 is our additive identity. When we do 0 XOR 1, we get 1. Because I mean, if you don't remember exclusive or, right? It's either this or that, but not both and not neither, right? So that's the only way. It's or, but it's exclusively either or, not and. So when the bits are not the same, we set it to 1. So, but if there's only two options, right? 0 and 0, 0 XOR 0 is 0, 0 XOR 1 is 1. So XOR does fit the bill for additive identity. Now the coolest thing about XOR is the additive inverse. And the additive inverse says that whatever thing you XOR with, it needs to equal the additive identity. So what elements is going to XOR with A to give us the additive identity?
Thing itself.
It's the thing itself, right? And this is a fact. This is actually a trait about the integers mod 2.
I hate to interrupt, but I've got to get to these bathrooms now. So somebody needs to go. Now's the time.
Sure.
Second of all, is I'm going to close this door because the vacuum.
Okay, thank you.
Don't interrupt.
Thank you, appreciate that.
Thanks.
All right, so this has to do with modular arithmetic in the integers. Actually, the Z mod 2. Yes, what Sasha said was exactly right. Itself is the additive inverse. So we do satisfy all three of those properties. So XOR is a viable operation to do a prefix table over. So let's continue. So we started here. Let's add an A, right? So we're going to XOR 1 with A. That's going to bring us back to 0. We're going to have 0 here. C, boom, that brings us to 4. Add an A, that brings us to 5. Add another C, back to 1. Okay, so we now have this kind of cryptic prefix table that's going to be providing us with the parities of each prefix. Now, you'll probably notice already that the only prefix that is an even substring is ABA, and look at that. It's precisely 0 at that point, right? So the next trick follows from the original prefix table. If we want to find the evenness of any arbitrary substring, not just a prefix substring, we're going to do the same idea. We're going to let's say I wanted to query between I want to see if this guy is even, right? Well, I can just take this guy, which is 1, and I can XOR it with this guy, which is 1. Now, why am I using XOR again? Well, remember, XOR counts because everything in mod 2 with XOR is its own inverse. That means that XOR operates as addition and subtraction simultaneously, right? So the idea of subtracting this segment from this segment is just the same operation. It's going to be another XOR. So 1 XOR 1 is going to give us 0. And that checks out, right? AC is going to be an even substring. So cool. We found an O of 1 way to figure out the parity of a substring. Okay. But that's not what the question is asking. The question wants to find the counts of these arbitrary substring. So specifically, remember, for any arbitrary substring, we need to find all of the even substrings inside of that interval. Okay, so what will that look like? Well, so we have our prefix guy. So why don't we need to return we need to both query and update the number of counts of these guys. So what should that, what if that rings a bell, that should be indicative that we need to be using segment tree over the number of even substrings. So what does that look like? Again, I don't know why I erased things so prematurely. I can still see this over here. I'll write it again. So we have our M, we have our A, B, B, A, C, A, C, and we have our 0, 1, 3, 1, 0, 5, 1. Now, we basically are going to create a frequency table over every possible parity of a prefix, okay? So what that means is, for example, if a prefix has exactly an odd number of A's and even everything else, that's going to fit into its own bin. If it's going to have exactly an odd number of C's and an odd number of A's, and then everything else even, then that's going to fit into its own bin. So basically, if you get what I'm getting at here, we have 6 different distinct letters, and they all are going to have a parity, 0 or 1. So the total number of frequencies, total number of unique substrings in terms of their parities is going to be 2 to the 6. Does that make sense? You understand why? Because each, like if I were to do it with 3 letters, A, B, C, right? If I want to keep track of the individual, unique, distinct substrings, then um, I need to have 8 slots, right? I need 1 slot for nothing, right? I need 1 slot for just A is odd. I need 1 slot for just B is odd. I need 1 slot for both are odd, and so on and so forth, right? So you can see I'm just enumerating over this bit string. So if you have n bits, you have 2 to the n possible combinations of these parities. So 2 to the 6 is 64. We're going to have so instead of storing the mask as the leaf nodes of our segment tree, we're going to store a 1-hot encoding of the prefix mask into these 64 bins. So a 1-hot encoding just means that, for example, 1 is gonna exist in the 1 slot, 3 is gonna exist in the 3 slot, 5 is gonna exist a 1 in the 5 slot. So we're basically taking a number and we're like flattening it out all the way up to its 2 to the 6 possibilities, right? Does that make sense? I'll show you what. So again, we have, I'm forgetting 4 in there. So we have 1, 2, 3, 4, 5, 6, 7, 8 nodes already. So we don't have to do any padding actually. We're going to include this 0 here. So what does that look like? I'm not going to write 64 bins here for each thing, but we're actually only working with 3 letters right now. So I'm just going to work with 3 bits just for now. So actually, I could write the hex instead, but let's just draw this out. I'm going to draw it out in binary just because it'll be really easy to see what's going on. So we need 0, 0. Okay, except for the leaf nodes, I'm just going to write their actual number because there's too many. So it's going to be 0. I guess I should start from the top. Let's put it right here. And then there's going to be 3 layers total, so this is fine. Or no, it's not fine. So M is our parity mask, and what it means is at a specific index, we're asking about um, the odd or the parity of the prefix string at this point. So this says 1, right? But what is it really referring to? If we have 3 characters total, it's referring to 0, 0, 1, where A belongs in the first slot, B belongs in the second slot, and C belongs in the third slot. So for example, 3 says that we have an odd number of A's and B's. So this is saying B is even, C is even, A is odd. This is saying A is odd and B is odd and C is even. So we're compressing the information down into the bits of a number. So this 3 is not really representing 3, it's representing a parity, a running parity over this entire prefix. So, okay, please do not do because I need to sum these two, so 2, 4, 6, yeah, okay. So we're gonna have 0 here, 3 here. Actually, I'll write the 3 bits out, but I'll only write 3 bits. So 0, 1, 1. No, sorry, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, and 0, 0, 1. Is everybody following how I got from these numbers to these numbers? This is just a binary. These are the bits. And this should make it more clear what I'm talking about. This is the empty string. This is A. This is AB. There's AB has an odd number of A's and an odd number of B's in it, right? So should make sense. Now, what we're going to do is, in reality, these will be decomposed into their bins as well. So you'll just get a value in the 1 hot encoding slot. So now I'll show you what 1 hot looks like. So we've got 1 count of 0, that's going to go here. We've got 1 count of 1, that's going to go here. We've got 1 count of 3. We've got 1 count of 1. We've got 1 count of 0. We've got 1 count of 4. We've got, yes. We got 1 count of 5, and we got 1 count of 1. 1 count of 1. 1 count of 1.
How are you picking the space out?
So it's just think of it as left shift by this amount, by this number.
Yeah, so for like if we have 0, 1, 1, that is 3, right? So we're gonna put it.
So we're gonna put 1 on left shift 3.
Yeah. So we have 1, 3.
That's what a 1 hot is. That's what a 1 hot encoding is. And then we could just fill the rest, right? But if it's not there, then it's a 0. So now let's do it again. So we got 1 here, 2 here, 0 here, 1 here, and then zeros all the way down from there. From here, we've got 1, 1, 1, 1, and then a 0, and then another 0. Wait, we have 1, 1, 0, 0, 1, 1. Cool. And then finally, we bring these guys up to. Wait. Am I doing this right? There's a 0 here and there's a 0 there, so that does make sense. And then 3, and then 0, 1, 1, 1, 0, 0. So that's our. So just to recap what this means, right? So this guy says over this entire interval, right? We have 2 prefixes that have length 0 or width. See, now that's not correct. So what did I do wrong? Oh, including the empty string. Yeah, there's two zeros here. There's two zero prefixes. There's two prefixes like 0. There is 3 prefixes with parity 1, 1, 2, 3. 0 with parity 2, and so on and so forth. Then I got 1, 3, 1, 4, and 1, 5. Okay? So now if the question was how many even prefixes are there, right? We should just return this value, right? Because we just did that work, right? If we wanted to find how many even prefixes are there over this range, including the empty string, there's 1, right? Over the entire thing, we've got the empty string and we've got A, B, B, A, right? So the if that was what it was asking for, the number of even prefix strings, then it's going to be just this value right here. But that's not what it's asking. It's asking for the total number starting from anywhere, not just prefix, starting from anywhere inside that range. So the last piece of the puzzle is how do we get these arbitrary substring kinds? And the way that it works is, let me just remind myself. Yes, so okay, so if we have, this is a good example. If we have 3, so in this example, we have 3 prefixes of length 1. Oh, sorry, not of length 1, of parity equal to 1, which corresponds to everything is even except for A. That's what this guy means. So let's find those prefixes, right? Well, we've got A, we've got A, yes, A, we got A, B, B, right? A, B wouldn't work because then B is also odd. So A is trivially going to be the only one because there's nothing else. A, B, B, B is even here, so that works. We're still going to only have A as odd. And then finally, we're going to have A, B, B, A, C, A, C, right? Because C is even, B is even, A is odd. So this number 3 corresponds to these 3 prefixes. Okay? Now, if I were to take this prefix and subtract it from this prefix, that's going to eliminate the odd A. You see? So what did I just do here? Remember, with the prefix table, we can do this. We can subtract prefixes to get arbitrary ranges. So if we find all of the prefixes that have exactly 1 and we subtract them from each other, we're going to get an even substring, right? Does that make sense? So like remember this had parity 1. We removed this guy. It now has parity 0. Similarly, I could do the same with this. I could do the same with this prefix. Remove him from this guy. And again, we have another different prefix that is of even parity, right? AC, AC. So if we have 3 unique prefixes that all share the same parity, the total number of even arbitrary substrings that they generate is all the different subtractions that I can do, right? So for a subtraction, I need 2 elements, and I have a total of 3 elements. So if I have 3 elements and I need to choose 2, what's the total number of ways that I can subtract these 3 elements? 3 choose 2, right? Otherwise known as, so n choose 2, right? For a n being the number of prefixes here, this value here, which is also equal to, if you didn't know this is pretty important to know. N choose 2 is equal to n times n minus 1 equals 2, which is also equal to the sum of natural numbers up to n minus 1. So we don't need to do the whole binomial coefficient drama. We just use this closed form for it instead. So that's the idea, right? So the final piece of the puzzle is for any set of prefixes that share the exact same parity, we can subtract them to generate a substring that has even parity. And the total number of ways to do that is going to be n choose 2 for all n in this bin, this histogram. So the and you know 1 choose 2 is impossible, so we're just going to return 0 for those. And so what we end up with is 2 choose 2. How many ways is there to choose 2? 1. And 3 choose 2. How many ways is there to choose? 3, right? This one, and this one. And that gives us 4 ways, which if you remember from the beginning, that corresponded to this one, this one, this one, and this one. So after all that, we have created a way to, now remember, the updating and the querying looks exactly the same as the segment tree that I showed you earlier, right? Because this is just addition, right? But it's element-wise addition over independent, it's element-wise, so over a vector, so each addition is independent of each other, right? So it's literally just the exact same as a regular sum prefix tree or segment tree. But now, instead of returning just the number of even prefixes, we're going to return the total number of even substrings. So that's how you solve the even substrings problem. And not only that, but you can query and update in log of n. So it takes n log n to build a segment tree, and q log n for the number of queries. So 2 passes of n log n, we're going to call that algorithm of n log n. Any questions? Anybody want me to go over something again? Or I think I'm over time by a little bit, but anyways, I thought this problem was super fascinating and like really freaking genius. So, well, if that's all, then
Staying a little longer, could you go through how those brackets worked again? Like how you decided the spacing of the therapist?
yes. So you mean how much space we allocated for each of these bins here? Like how many bins per thing here?
I guess I mean like how did you generate it, or what was the process behind it?
So this guy is giving me the sum of all of the unique. So it's like a frequency map, right? We're saying there are 3 prefix strings, right? So from 0 to I that contain an odd A and even everything else. Everything else shows up an even amount of times. A shows up an odd amount of times. That's what this says, right? And over the entire thing. But it's actually really composed over the guy who asked the same question, this guy and this guy, over these 2 smaller intervals. Okay? So this guy, because remember, because XOR, or sorry, this is sum. Because sum is associative, addition is associative, it's okay that we're able to just add them like this, 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 and then this, right? That's not always a given, right? If your binary operation requires a specific order to work, then this will break because you don't know, like if I were to query these guys, then it's going to be like this guy plus this guy plus this guy, and so on and so forth. You said, does that answer your question? What was the other part? You said,
So
what do they represent? Yeah. So does that make sense? Do you understand the prefix parity idea? Because there's a lot of like layered ideas on there. So feel free. There's no dumb questions. Just
it's okay. It's just taking a while to see it.
no. That's totally fine. Like
What's the formal name for this process so I could look it up later?
Which process?
Or
The,
like, I guess the step.
the tree?
Yes?
Yes, so that's a segment tree.
Okay, so it's just part of.
So a segment tree, all a segment tree says is that you're going to, you have some data, okay? You want to query it fast and you want to update it fast. And you need, so for your data, you need to have, it needs to be associative, because remember, I need to be able to apply the operation in any order. And it also needs to have an identity element, so that I can pad it out so that we can get our perfect binary tree. So the segment tree just doesn't care what the data is, doesn't care what the operation is besides those two things, and then it literally just splits it up like this. Because now what we're saying is, the key idea is, right, it's gotta be a perfect binary tree. What we're saying is now, because we can just accumulate over these smaller intervals, this guy contains all of this information, but it's composed, it's binary decomposed upwards and outwards like this. That's like the main idea of the segment tree, because remember, if we had just done a regular prefix table, then updating, right, would be O of n worst case. But now with the segment tree properties, updating, you only have to propagate, if I update this guy, I only have to update this guy and this guy and this guy, instead of the whole table. For small tables, it may not be as clear cut as to why that is beneficial, but if you have 200,000, if your string is 200,000 or your data is length 200,000, then log of 200,000, I don't even know. That's much smaller.
How do you update the tree
For this guy specifically?
Yeah.
So it'll just be the exact same as any. Actually, no. This is a good question, because if I do, this is what I didn't go over. It's smaller detail, but how it works is, it's actually not a small detail. I just didn't cover it because I didn't have time. But so let's say we have a change from, let's say we modify. I'm gonna put the characters behind, underneath them. Okay. Right, but remember, this guy doesn't correspond to A. He corresponds to the whole thing, up to and including A. Okay. So let's change this C. I'm not gonna erase it actually, because we're gonna need both. Let's change C to be A. So what did we just do?
one to subtract the one from the B place and add one to the A place.
That's correct. That's essentially exactly right. So how that looks like is we're going to create something called a tag. It's just called a tag, but we're going to take the C's place, we're going to set it, B's place nothing, and we're going to set the A's place. Okay, this is our tag. And what this is going to do is, so here's all of the bins. So all of the bins, because the bins, there's multiple bins in here that contain an odd C, right? There could be the one where it's just odd C, nothing else. There could be one where it's odd C and odd A and odd B, right? So there's multiple bins that are going to be with odd C that need to be changed, right? And so all of the prefixes that had, so what was it before? What was our C before? We had, so this is an odd C, and even everything else. So all of the things that had odd C in them now need to be replaced with everything that had even C in them, and everything that had odd or even A in it now needs to be replaced with everything that had odd A in it, because the it exactly swapped, right? We flipped a bit of C and we flipped a bit of A. So if all the prefixes that contain an odd, all the prefixes that contain an odd C and an even A need to become like the number of those is now going to be replaced with the number of prefixes that have an even number of C's and an odd number of A's, right? Because we just flipped A to be odd and C to be even. And the same goes true for all of the even A's and the odd A's. So this is highly non-trivial, but what it looks like is, so like we can draw it out. So if I have A, B, B, A, C, right? We're gonna have I guess the relevant ones are, we have C is 4 and A is even, so that's 0, right? This substring has all even in it, and this substring is all even except for C. So it corresponds to 4 and 0. When I change this to A now, so 4, index 4 is holding 1, index 0 is holding 1. Now when we set it to A, B, B, A, we need to, whatever was the number of prefixes that contain this C, which was contain exactly C and everything else even, is now going to be modified to have an A. Actually, in order to make this a little bit more clear, like let's go to A, B, A, C, A, and change it to A, B, B, A. So that switches things, right? So now we have both an odd C and an odd A. So that's going to give us 5. Let's just write 1, 0, 1. Okay. When I switch this to A, we're now going to have 0, 0, 0. So these get flipped. They get flipped. And what that means is all of the things that were in all of the prefixes. So let me, okay. This prefix change affects this guy, but it also affects everything beyond it. Okay, right? Does that make sense? So we need to encapsulate all that information. So right now we said we had 1, 0, 1. So this prefix has this has 1, 0, 0, right? And now it changed to 0, 0, 1. And this guy changed from A, B, B, A, C, A. This was 1, 0, 1 to 0, 0, 0. Okay? The number of, let's say there was some number of, like the bin isn't just 1. The point I'm trying to get at is that when you swap the two, when you flip the bits like so, you are essentially swapping the number of elements, the number of prefixes with that specific parity with whatever bin that has this parity. So look, these parities swapped. So there, and this bin had 1 in it. This bin had 1 in it. And this bin has 0 in it. Okay? So when we do the flip, the bins are also going to swap. Does that make sense? That's what I was trying to say. Like all the things that contained exactly 1C and 1A from here and beyond, like so, they are also going to have to get updated. So in that case, let's see, 101 had 1, and 101 had 1, and 000 had 0. But then when we do the swap, we're going to swap their bins as well. So when you update a value, like how we just did from C to A, the only thing that happens is we swap the relevant bins. So that's what the update looks like. So thank you for asking that, because that isn't, you're right, that is not trivial. The building is trivial, but the updating corresponds to a permutation of the histogram, because precisely the number of things that is created is the number of things that is destroyed, right? The number of you lose 1C, you lose the parity of 1C, and you gain the parity of A. So all of the parity A things swap with all the parity C things. If you want to learn more about it, just look at the GitHub. It'll have the annotated code. But yeah, I went way over. But is there any other questions? Anybody worried about anything else? Didn't understand?
Are you open to questions during the week or with?
Yeah, DM me. That's totally fine.
Or put stuff in the chat.
Yeah, throw it in general, and other people can see our conversation, or they can provide help as well.
Thanks for taking the time to do this.